Far beyond Earth, the universe keeps one quiet rule. Light sets the limit. No ship, no engine, and no human journey can truly pass it. But as a spacecraft moves closer and closer to that boundary, time begins to slow, distance begins to change, and the stars themselves no longer look the same. Tonight, this video follows the real science of what happens near the speed of light. If these calm space documentaries help you relax, please like the video, subscribe to the channel, and enjoy the journey. Space seems open and silent, but physics does not treat it as an empty stage where anything may happen. It treats space and time together as a single structure, often called space-time, within which every event takes place. In that structure, light is not merely one fast traveller among many. Its speed in vacuum appears as a built-in feature of nature, the same for all observers who measure it locally. This is the broad law that governs the whole subject. The speed of light, close to 300,000 kilometers per second in empty space, is not presented by modern physics as a technological barrier waiting to be overcome. It is presented as a limit woven into the geometry of reality itself. In older ways of thinking, motion seems simple. A carriage moves along a road, a ship moves across water, a planet moves across the sky. Speed looks like nothing more than distance divided by time, and in ordinary life that is enough. Yet light does not fit neatly into that older picture. Careful experiments and Einstein's special relativity lead to a different view. They show that the measured speed of light in vacuum does not add up in the ordinary way when observers move relative to one another. Instead, space and time adjust so that this speed remains fixed. The result is not a small correction to common sense. It is a change in the underlying description of motion itself. The universe allows many speeds, but it organizes them around one invariant speed that matter may approach and never attain if it has mass. This gives light a special place in nature. A beam of light does not carry an ordinary rest frame in the way a ship or a stone does. It marks the boundary between what can be connected by slower travel and what cannot. In relativity, this boundary helps define cause and effect. One event may influence another only if something travelling no faster than light can pass between them. In that sense, the speed of light is not important only because light itself moves that quickly. It is important because information, influence, and physical connection are constrained by the same limit. The law is therefore deeper than astronomy, deeper than engineering, and deeper than the practical problem of building a fast vehicle. It belongs to the basic order by which the universe remains consistent. At the scale of daily life, this law hides its strangeness. Human beings move slowly compared with light, aircraft, rockets, and planets all inhabit a realm where relativistic effects are usually too small to notice without careful instruments. Because of that, ordinary intuition grows out of a slow world. In that slow world, one may imagine adding speed as though stacking one gentle motion on top of another until a final destination is reached. Relativity does not permit that picture to extend without limit. As speeds rise toward the cosmic boundary, the familiar rules of addition and the familiar sense of a universal ticking time stop serving as faithful guides. The speed of light stays fixed, and the rest of the description must bend around that fact. For a massive object, this leads to the central physical conclusion. A thing with mass may be pushed faster and faster, but each further gain becomes harder to achieve as the motion draws closer to light speed. Modern explanations often describe this by saying that the energy required rises without bound. and that reaching the exact speed of light would require infinite energy. The language may vary between textbooks, but the physical message remains the same. Nature does not offer a final crossing point for ordinary matter. The limit is not crossed by a stronger engine, a larger fuel tank, or a more refined machine if the traveller remains a massive object moving locally through space-time. In this framework, approaching the boundary is allowed. Becoming light-like is not. This does not mean the universe lacks motions that seem faster than light when described carelessly from far away. The expanding universe provides an example. Distant galaxies may recede from one another faster than light because the amount of space between them grows. That does not mean one galaxy is locally outrunning a beam of light through its nearby space-time. The distinction matters. Relativity constrains motion through space-time in a local sense, while general relativity allows space-time itself to stretch. The apparent exception, therefore, leaves the deeper rule intact. The cosmic speed limit still governs what any object may do in its own neighbourhood, where clocks, rulers, particles, and light can be directly compared. The same care applies to popular ideas about shortcuts. Warp drives and wormholes belong to the language of general relativity. But in serious physics they remain speculative constructions with severe problems. The known proposals require conditions such as exotic forms of matter that have not been observed in the needed way, and there are strong reasons to doubt that such ideas provide a practical escape from the light speed limit for ordinary travel. For the calm outer view of this topic, the important point is simple. Modern physics does not present a clear, tested loophole through which a massive spacecraft may ignore relativity and pass freely beyond the speed of light. After many experimental checks, the limit remains one of the most stable features in all of physical theory. Seen from this widest region of the subject, the speed of light is therefore not just a number associated with bright things in the sky. It is a structural boundary that shapes measurement, motion, causality, and the meaning of distance and duration in the physical world. It tells physics where matter ends and radiation begins in a very deep sense. It also explains why the dream of simply reaching light speed carries more than mechanical difficulty. The dream runs into the architecture of space-time itself. Within that architecture, light occupies the boundary naturally, massless and unburdened, while matter remains forever on the slower side of the line, able to draw nearer and nearer, yet never to arrive. Motion never appears alone. It is always described relative to something. A drifting spacecraft is said to move relative to a planet. A planet moves relative to a star, and a star moves relative to the centre of its galaxy. This seems ordinary at first, but in relativity, it becomes the foundation of the whole description. A reference frame, defined simply, is a way of assigning positions and times to events so that motion can be measured. Without such a frame, a statement about speed remains incomplete. Physics therefore begins this region of the subject by asking not how fast something moves in an absolute sense, but relative to what it moves. This change matters because ordinary language often suggests a hidden stillness somewhere behind all motion. It is easy to imagine that the universe must contain a final background, a perfect stage that decides what is truly moving and what is truly at rest. Special relativity does not grant that privilege to any frame moving steadily without acceleration. Such frames are called inertial frames. In simple terms, an inertial frame is one in which a body left alone continues in a straight path at constant speed. Within such frames, the laws of physics take the same form. No inertial observer may perform a local experiment and discover a unique state of absolute rest. Rest always belongs to a chosen frame, never to the universe as a whole. This idea is not a poetic statement about perspective. It is a physical rule with measurable consequences. If two spacecraft glide past one another in deep space, each moving steadily and without rotation, each may treat itself as at rest for the purpose of describing nearby events. Each sees the other as moving. This symmetry is not a trick of language. It reflects the structure of the laws themselves. One frame is not more correct than the other merely because a human mind prefers one viewpoint. What changes from frame to frame are the assigned values of position, duration, and speed for many events. What remains unchanged are the underlying laws and the constant speed of light in vacuum. At slow speeds, the differences between frames appear mild. A ball thrown inside a train may be described one way by a passenger and another way by an observer standing beside the track. Yet daily life remains orderly because the differences follow familiar patterns. Velocities seem to add in a straightforward manner, and time seems shared by all. Relativity enters when the calm picture meets light. The measured speed of light does not behave like the speed of an ordinary thrown object. It remains the same for all inertial observers. This is the crucial fact around which the rest of special relativity is built. Once this fact is accepted, the older idea of universal time can no longer remain untouched. To preserve the same light speed for all inertial observers, nature does not alter light to suit each observer. Instead, space and time themselves must be measured differently in different frames. Events that appear simultaneous in one frame need not appear simultaneous in another. Distances along the direction of motion and durations between events no longer remain fixed for everyone. These are not distortions caused by bad instruments or delayed signals. They are part of the lawful geometry of space-time. The reference frame chosen by an observer shapes how measurements are assigned, and the assignments differ in precise and predictable ways. Even so, relativity does not dissolve reality into confusion. It does not claim that anything may be true from one angle and false from another without limit. It says something more disciplined. Each inertial frame provides a valid description, and transformations connect one description to another in a consistent way. If one observer measures a particle moving steadily, another observer in uniform motion may compute a different speed, but both remain linked by the same mathematical structure and the same physical law. The disagreement is controlled, not chaotic. Relativity replaces the old universal stage with a set of equally valid steady frames, each partial on its own, yet fully compatible with the others. This also clarifies what acceleration means. A steadily moving observer may regard itself as at rest, but an accelerating observer cannot hide acceleration in the same way. Acceleration produces measurable effects inside the frame itself. Forces are felt. Instruments detect the change. A person in a turning or speeding vehicle senses that the frame is not inertial, for the present region of the subject. This distinction is important because the dream of extreme speed often begins with a confusion between constant motion and changing motion. Relativity treats them differently. Uniform motion allows symmetry between observers. Acceleration breaks that symmetry in direct experience. In the broad calm of interplanetary or interstellar space, this means there is no cosmic marker that labels one smooth traveller as the one truly at rest. One may choose the sun as a convenient frame, or Earth, or the centre of the Milky Way, or the frame in which the cosmic microwave background looks nearly even in all directions. These choices may be useful for astronomy, but none restores an absolute rest in the sense rejected by special relativity. They are practical choices, not final truths. Physics may prefer one frame for a calculation, yet nature does not crown it as the frame behind all others. Seen from this layer of the topic, the meaning of motion becomes quieter and more exact. To say that a craft moves at a certain speed is always to place that statement inside a frame. To say that light has the same speed for all inertial observers is to accept that measurements of space and time must adjust accordingly. To say that no absolute rest exists is to accept that the universe does not provide a hidden still platform from which all true motion is judged. These ideas may seem abstract, yet they form the ground beneath every later effect of relativistic travel. Before energy rises, before clocks drift apart, before light changes its appearance, the first inward step is simply this: motion belongs to relations between observers, and the laws remain the same in every steady, unaccelerated frame. A spacecraft moving through deep space enters a region that appears almost empty, and in many practical ways it is. There is no breathable air around the hull, no wind pressing against the surface, no clouds, no weather, and no ground to define up or down. The familiar features that shape motion on Earth fall away. Space does not provide a surrounding fluid in the ordinary sense, so a craft travelling steadily does not need constant thrust merely to keep going. Once set into motion, it continues in motion according to inertia, carrying its speed through a vast darkness that offers almost nothing to push against it. This emptiness is often called a vacuum. A vacuum means a region with very little matter in it, not a region with nothing at all. The distinction matters. In laboratories on Earth, even carefully prepared vacuum chambers still contain some particles. In space, the vacuum is usually far better than anything easily produced on the ground. Yet it is still not perfect. Between planets there are scattered atoms, ions, dust grains, sunlight, magnetic fields, and streams of charged particles flowing outward from stars. Between stars, matter becomes thinner still, but it does not vanish. Space gives the impression of pure absence, yet physics describes it as an extremely low-density environment rather than a true void. That low density changes nearly every practical feature of travel. In an atmosphere, movement is shaped by drag, the resisting force caused by air. Wings function because air flows around them. Engines that depend on oxygen require the surrounding gas. Sound travels because air or another material carries pressure waves from place to place. In vacuum, none of this occurs. A spacecraft has no aerodynamic lift, no ordinary engine intake, and no external medium to carry sound. The hull may vibrate, machines may hum inside, and structures may transmit those vibrations through metal. But outside the craft there is no air to convey them onward. The surrounding space remains silent in the usual human sense. The absence of air also changes the meaning of temperature. On Earth, warm air and cool air move heat around by convection, while physical contact moves heat by conduction. In vacuum, convection disappears because there is no surrounding gas to circulate. Conduction across empty space also disappears, because there is no material bridge between one object and another. Heat still exists, but it moves mainly by radiation, meaning electromagnetic waves such as infrared light. A spacecraft in sunlight may warm where light falls on it, while shaded parts may cool by radiating energy away. Deep space is therefore not simply cold in the ordinary sense of being filled with freezing air. It is a place where heat exchange happens in a different manner, quieter and less intuitive. Light becomes the dominant presence in this apparent emptiness. Sunlight crosses interplanetary space without needing a material carrier. Starlight crosses interstellar distances in the same way. A craft travelling through vacuum is bathed not in air but in radiation. Some of that radiation arrives as visible light, which gives shape to planets, moons, stars, and dust. Some arrives beyond human sight in infrared, ultraviolet, X-rays, radio waves, and other parts of the electromagnetic spectrum. Space may look dark because matter is sparse, but light still threads through it continuously. The darkness of space is not the absence of light everywhere. It is the absence of nearby material dense enough to scatter light into a bright sky. This is why the sky seen from open space differs so much from the sky seen from Earth's surface. On Earth, molecules in the atmosphere scatter sunlight, producing a blue daytime dome and soft gradients near the horizon. In vacuum, with no thick atmosphere to spread light around, the contrast grows harsher. A sunlit object may blaze while the background remains black. Shadow may appear immediate and deep. The emptiness around the craft does not soften illumination. It does not blur distance. It lets light travel in straight lines across enormous reaches, revealing some surfaces clearly while leaving others in darkness. Even in this sparse environment, gravity remains present. Vacuum does not mean freedom from gravitational influence. A spacecraft between worlds still moves through the curved gravitational landscape created by stars, planets, moons, and other masses. The surrounding region may seem empty to the eye, yet motion through it is shaped by invisible geometry. Orbits are traced in vacuum. Tides act across vacuum. Planetary systems hold together across vacuum. The absence of air, therefore, does not mean the absence of structure. Space still has order, direction, and influence, only expressed through fields and geometry rather than through wind, pressure, and terrain. The vacuum around a craft also changes human orientation. On Earth, up and down are guided by gravity and by contact with the ground. In free space, those cues weaken or vanish inside a steadily moving vessel. The outer environment offers no natural horizon unless a nearby planet, star, or disk of dust provides one. A craft may be rotated in any direction and continue on the same path. The emptiness outside does not care which wall is called the floor. Direction becomes a matter of internal design and chosen reference, not of the surrounding medium. At larger scales, the same quiet sparsity continues. Interplanetary space contains the outflow from the sun, scattered debris, and the broad reach of the solar magnetic field, yet it remains astonishingly thin compared with any atmosphere. Interstellar space is thinner still, with lonely atoms spread across immense distances, mixed with faint dust and diffuse clouds in some regions. Between galaxies, the average density falls even further. Across all these domains, the craft moves not through a dense ocean, but through a near emptiness so deep that everyday intuition struggles to picture it. Human experience grows in crowded environments full of surfaces, fluids, and resistance. Space removes almost all of those companions. Seen from this region of the subject, the route toward extreme speed begins in a setting defined less by what surrounds the craft than by what does not. There is no air to roar around the hull, no steady friction to slow a coasting vessel, no sky to brighten the void, and no ordinary medium to carry sound or convective warmth. Yet the vacuum is not a perfect nothingness. It contains sparse matter, radiation, gravity, and fields, all spread thinly across enormous distance. The craft therefore travels through a realm that is almost empty, but not truly blank. A realm whose quiet simplicity makes spaceflight possible, and whose subtle contents still give the voyage its physical meaning. A fast journey does not begin with speed alone. It begins with a change in speed, and that change is acceleration. Acceleration means that velocity changes over time, either in amount or in direction. A craft resting beside a launch platform, orbiting a planet, or drifting in deep space must accelerate if it is to move faster than before. This is the first practical threshold in any serious discussion of extreme travel, long before relativity reshapes time and distance in dramatic ways. The simple act of gaining speed places demands on the machine and on the living body inside it. A speed close to light speed is not reached by quietly selecting a higher number. It is approached only through sustained acceleration, and sustained acceleration is not a gentle condition for human survival. On Earth, people know acceleration through ordinary experience. A car pulls away from a stop and presses the body into the seat. An aircraft climbs and the body feels heavier for a short time. A turning vehicle pushes the body sideways. These are mild examples, but they show the same principle. In the frame of the accelerating vehicle, the body feels a force because each part of it resists the change of motion. Organs, blood, bones, muscles, and connective tissue do not begin that change with perfect uniformity. They are held together and carried along by physical structure, and that structure can be strained. The feeling of weight in such moments is not quite the same as gravity, yet it can resemble gravity closely enough that the body responds in related ways. For short periods, a healthy person may withstand a moderate acceleration well. Pilots and astronauts endure brief intervals of stronger acceleration with training, special seating, restraint systems, and careful support. The problem changes when the acceleration lasts longer. What matters is not only how strong the acceleration becomes, but how long it continues and in what direction it acts through the body. A force pushing from chest to back is tolerated differently from a force pushing from head to feet. The body depends on circulation, and circulation depends on pressure distributed in a workable way. Under significant sustained acceleration, blood tends to shift, pooling away from the brain or pressing unevenly through the chest and abdomen. Vision may narrow, awareness may fade, and tissue may be placed under stress even before any injury becomes visible. This is why the first real danger in a near light speed journey is not the distant abstract limit set by relativity, but the much nearer biological limit set by the body. A machine may in principle keep accelerating for a long time if it has power and structure enough. A person inside that machine remains a soft, fluid, living system with narrow tolerances. The heart must keep moving blood. The lungs must expand and contract. The brain must remain supplied with oxygen. The inner ear and nervous system must continue to function under unusual loads. Even when no part of the body breaks, performance may decline rapidly if the acceleration is too strong or too prolonged. A calm and realistic journey therefore favours modest acceleration, something closer to the weight that human beings already know at Earth's surface, at around 1 Earth gravity, sustained over a long interval. The body may continue to function in a comparatively stable way if the support system is well designed and the body is properly aligned. This is one reason such a value often appears in serious discussions of long, relativistic voyages. It is not magical, and it is not effortless, but it sits near the range of human familiarity. A traveller under this steady push would feel not weightless drifting, but something closer to life on a planet with a floor beneath the feet. The cost of such comfort is time. Even a gentle acceleration carried on for many days, weeks, or months builds speed slowly compared with the enormous scale of light speed. This reveals a quiet truth that often disappears in dramatic storytelling. To reach an extreme velocity without harming the passengers, acceleration must usually be limited. If acceleration is limited, the period of speeding up becomes long. A near-light speed mission is therefore not simply a problem of powerful engines, it is also a problem of patience, endurance, and biomechanical restraint. The body acts as a governor on the journey. It places a ceiling on how rapidly the voyage may unfold if the travelers are to remain alive and functional. The internal design of the craft must serve this biological need. Seats or couches must support the body so that force spreads across a broad area rather than concentrating on a few points. The preferred body orientation matters because force carried through the chest differs from force carried from head to foot. Fluids may need careful management. Muscles may require regular activity. Medical monitoring becomes essential, not because the journey is violent in a cinematic sense, but because even orderly acceleration can become dangerous through accumulation. A day of moderate loading differs from a month of it. A month differs from a year. The body does not experience duration as an engineering note in the margin. It experiences duration as a continuing physiological condition. Acceleration also reshapes the interior meaning of direction. In a coasting spacecraft far from strong gravity, up and down are matters of convention. Under constant acceleration, a floor and ceiling regain meaning. The direction opposite the thrust feels like down because the ship continuously pushes into the bodies it carries. Water settles, objects fall, and movement through the cabin begins to resemble motion inside a gravitational field. This resemblance is not accidental. Einstein's equivalence principle expresses, in simple terms, that acceleration and gravity can be locally similar in their effects. For the traveler, the distinction may matter less in daily experience than in theory. What matters directly is that acceleration turns the interior of the craft into a place with felt weight again, and that weight must remain within tolerable bounds. There is also the problem of starting and stopping. A long voyage to high speed requires not only acceleration away from the starting point, but, for any meaningful arrival, deceleration near the destination. The body must endure both phases. The full mission profile therefore includes 2 extended intervals of load, not 1. If the spacecraft flips and thrusts in the opposite direction to slow down, the passengers still feel sustained force, only reoriented within the ship. The journey becomes a carefully managed passage through prolonged artificial weight, not a single dramatic burst followed by uncomplicated rest. Seen from this layer of the subject, acceleration is the first inward narrowing of possibility. The vacuum outside the craft may seem calm, but the bodies within it cannot ignore the method by which speed is gained. Before the enormous energy cost dominates the analysis, before clocks drift apart and distances begin to shrink, the voyage must pass through this human gate. A near light-speed craft has to accelerate, and acceleration is never abstract inside a living body. It is felt in the blood, in the spine, in balance, in breathing, and in endurance. The road toward extreme speed therefore begins not with triumph over distance, but with a steady negotiation between motion and biology. Speed alone does not tell the full story of a fast journey. Behind every increase in speed stands a transfer of energy. A spacecraft does not move faster simply because it is pointed in a new direction, or because space offers little resistance. It moves faster because an engine or some other propulsion system gives it energy and momentum. At slow speeds, this relationship is already familiar. A heavier vehicle needs more effort to accelerate than a lighter one. A faster vehicle carries more kinetic energy, meaning the energy associated with motion, than a slower one. On everyday scales, these ideas remain manageable. A modest increase in speed calls for a modest increase in fuel or power. Near the speed of light, that calm pattern no longer holds. Relativity changes the cost of motion. As a massive object moves faster and faster, each further gain in speed demands more energy than the previous gain. This is not merely because the craft is already moving quickly. It is because the geometry of space-time does not allow matter with mass to slide easily toward the speed of light in the way common intuition suggests. The familiar habit of imagining equal pushes producing equal additions of speed begins to fail. A vehicle may continue receiving energy, yet the increase in speed becomes smaller and smaller as measured against the light speed limit. The closer the craft comes to that boundary, the harsher the energy demand becomes. This is one of the central reasons why reaching light speed is not treated as a difficult engineering challenge waiting for future refinement. It is treated as a physical impossibility for massive matter moving locally through space. The required energy does not merely become very large. In the idealized language of relativity, it grows without bound as the object approaches the speed of light. That means there is no final reserve tank large enough and no final engine powerful enough that turns the last approach into an ordinary step. The problem does not remain finite. Nature does not present a final price that might someday be paid. It presents a cost that diverges. At first this can sound abstract, but the practical meaning is simple. A spacecraft may reach a substantial fraction of the speed of light in principle, if enough energy is supplied and if many other dangers are solved. Yet every additional fraction becomes more expensive than the one before. The curve steepens. A journey from a low speed to a moderate one is demanding. A journey from moderate speed to a very high fraction of light speed is far more demanding. A journey from that point to a still higher fraction becomes so expensive that the numbers begin to escape ordinary human scale. The ship is not merely asking for more fuel. It is asking for a transformation in the entire meaning of what counts as an achievable energy budget. This difficulty can be described without mathematics by thinking in terms of diminishing return. Early in the acceleration, energy put into the craft produces a noticeable increase in speed. Later, large amounts of additional energy produce only a smaller visible increase in speed. Later still, the speed continues to creep upward while the energy demand swells enormously. The spacecraft does not stop responding. It simply responds less and less in the way common sense expects. This creates a quiet but severe barrier. A mission planner may imagine pushing from one fraction of light speed to a higher fraction, but the energetic cost of that decision may rise so sharply that the plan ceases to belong to any realistic civilization-scale engineering effort. The source of that energy also matters. Every propulsion system carries its own burden. Chemical fuel is familiar and useful for launch and ordinary spaceflight, but its energy density is far too low for relativistic travel by massive crewed craft. Nuclear fission releases more energy, and nuclear fusion promises still more. But both come with their own technical and structural demands. Matter-antimatter annihilation, in theory, releases energy with extraordinary efficiency, yet producing, storing, and handling antimatter at useful scales remains far beyond current practical ability. even if a very high energy source were available. The spacecraft would still face the problem of converting that energy into directed thrust with sufficient efficiency, while also carrying whatever fuel, engines, shielding, radiators, and support systems the voyage requires. This produces a second burden beyond the raw amount of energy needed. The ship must often carry the means of its own acceleration. Fuel has mass, tanks have mass, engines have mass. Structure added to support the fuel and engines has mass as well. That extra mass then requires still more energy to accelerate. The mission becomes caught in a compounding loop. To go faster, the ship needs more energy. To carry more energy, it needs more mass. To accelerate that extra mass, it needs yet more energy. This is one reason rocket design becomes so unforgiving even at much lower speeds. At relativistic speeds, the burden grows into something severe enough to dominate the entire concept of the vehicle. A beam-driven craft, pushed by energy sent from far behind rather than carried on board, seems to soften part of this problem. In such a design, a distant laser or other beam source transfers momentum to a light sail or related structure. This reduces the need to carry all acceleration energy as onboard fuel. Even so, the challenge remains immense. The beam must stay focused across enormous distance. The sail or receiver must survive the incoming power, and the total energy delivered must still be vast. The method may shift the location of the burden, but it does not abolish the burden itself. Relativity still governs the cost of approaching light speed. Heat adds another quiet tax to the problem. No engine is perfectly efficient. Whenever energy is handled in large amounts, some part of it usually ends as unwanted heat. In space, where cooling depends mainly on radiation, getting rid of that heat is not simple. Large radiators may be needed, and those radiators add mass and complexity. The faster and more powerful the vehicle becomes, the harder it may be to manage the waste left by its own effort. The dream of immense propulsion therefore carries a shadow of immense thermal management. Energy must not only be produced and directed, it must also be endured. Seen from this region of the subject, the approach to light speed is narrowed not by a dramatic collision with a wall, but by an ever-steepening demand. Each step upward in speed asks for more than the last step, and near the limit the asking becomes extreme. The spacecraft moves into a regime where energy no longer behaves like a large but familiar resource. It becomes the governing obstacle. This does not mean high-speed travel is meaningless. It means that the universe charges a harsh price for every approach toward its fastest boundary. A massive craft may continue to gain speed, but the cost rises without mercy, and that rising cost is one of the clearest signs that light speed is not a destination for matter, only a limit that matter forever approaches from below. A spacecraft under constant acceleration is not merely a shell moving through space. It becomes a structure carrying a continuous load from the engine or driving system, through the frame, across the hull, and into every tank, instrument, beam, joint, and attachment point. The thrust enters through a real place, passes through real materials, and produces real stress. Stress means force distributed within a material. If that stress is uneven or poorly directed, the craft may bend, twist, crack, or fail even while the acceleration itself remains moderate. A vessel meant to endure a long steady push must be light enough to be worth accelerating, yet strong enough to transmit that push safely for the full duration of the journey. This balancing act is already central to present spacecraft design. NASA structural standards describe load analysis as the calculation of loads, accelerations, and deflections across mission environments, including space operations after launch. ESA structural guidance likewise treats the spacecraft as a connected system whose design must be analysed, tested, and qualified with care. The same logic becomes even more important for a relativistic craft. Under long acceleration, every part of the vehicle must take its place in a load path, meaning the route by which force travels through the structure. If that path is inefficient, the craft wastes mass on reinforcement in the wrong places, or leaves weakness where the force is greatest. The first structural question is simple in wording and difficult in practice. Where does the push enter the ship? If thrust comes from engines mounted at the rear, then the rear structure must press forward on everything in front of it. If the ship is instead pulled by an external beam acting on a sail or forward structure, then much of the vehicle is loaded in the opposite sense. These details matter because materials often tolerate one pattern of loading better than another. Compression may lead to buckling, which is a sudden sideways failure of a part being squeezed. Tension may be easier to handle in some members, while joints and attachments remain vulnerable. A practical design must therefore shape the vehicle around the direction in which force truly flows. Stiffness becomes as important as strength. A structure may be strong enough not to break and still be too flexible for precise flight. Flexibility allows bending, and bending changes alignment. If a long craft bends under thrust, the engine may no longer point exactly through the centre of mass, which is the balance point of the vehicle. Even a small offset may introduce a turning effect that guidance systems then have to correct. Those corrections can produce additional loads and vibration. A stable high-speed craft therefore needs more than survivable materials. It needs an arrangement stiff enough to keep the line of thrust and the line of mass closely aligned over long periods. Vibration adds another layer. Real structures do not respond to force as perfectly motionless objects. They flex, ring, and oscillate. Every structure has natural modes of vibration, meaning preferred patterns in which it tends to shake. NASA load standards emphasize dynamic loads analysis because spacecraft respond to changing forces as elastic systems, and because those responses must be calculated rather than guessed. Damping, which means the gradual reduction of vibration energy, is also treated as something that should be based on measurement of actual structures or close experience with similar ones. For a craft under prolonged acceleration, vibration may come from engine pulses, pumps, rotating machinery, fluid motion inside tanks, or small asymmetries in thrust. If any of these repeatedly excite a natural mode, a modest periodic force may build into a much larger structural motion. The danger is fatigue, misalignment, loosened fasteners, and cracked joints. Mass distribution quietly governs all of this. A vehicle with its heavy components clustered near the main thrust structure is easier to support than one with large masses spread far from the central load path. A full tank behaves differently from an empty one. A vehicle whose mass shifts during the journey changes its balance and sometimes its response to vibration. Propellant movement inside partially filled tanks can create slosh, a delayed fluid motion that pushes back against the structure and complicates control. Instruments mounted far from the mainframe may amplify bending. Large, thin panels may save mass but flex too easily. The engineer therefore works not only with amounts of mass but with geometry. There is also the problem of connections. A spacecraft is assembled from interfaces, bolts, welds, brackets, mounts, seals, flanges, trusses, and bonded surfaces. These interfaces often decide the practical limit of the structure. A solid beam is only as useful as the way it is attached to the next component. Under long constant acceleration, tiny repeated motions at a joint may slowly enlarge into wear or creep. Creep means a gradual permanent deformation under sustained load. This matters especially when different materials meet, because metals, composites, ceramics, and seal materials may respond differently to stress and time. A vehicle intended for a long relativistic push cannot be designed as though brief launch loads are the only serious event in its life. Testing and verification become unavoidable because analysis alone is never enough. NASA standard stress representative models, approved methodologies, and repeated load cycles with uncertainty factors, acknowledging that even advanced calculations carry error. ESA guidance takes the same broad view by treating qualification as part of the design path rather than an afterthought. For a craft meant to accelerate for months or years, this logic deepens. Ground tests would need to examine not only maximum stress but long-duration behavior, resonance, joint stability, and tolerance to small off-axis loads. The structure would need margins not for one brief event, but for a prolonged campaign of force moving through the same skeleton day after day. Seen from this region of the subject, a near-light-speed spacecraft is not simply an engine with a cabin attached. It is a carefully managed chain of forces. The push begins somewhere physical, travels through a chosen load path, meets materials with finite stiffness and strength, excites vibrations, tests joints, and reveals every weakness in the arrangement of mass. A successful craft would need to be extraordinarily efficient in structure, neither overbuilt into useless heaviness nor underbuilt into fragility. Under constant acceleration, the ship becomes a mechanical conversation between thrust and matter, sustained without pause. The outer vacuum may remain quiet and almost empty, but inside the vehicle the force must be carried continuously through the body of the machine itself, inside a steadily moving spacecraft. Life may appear ordinary. A cup may rest on a table, a hand may move across a control surface, a person may walk the length of a corridor, and a clock may tick with its usual rhythm. Nothing in that local scene announces that time itself has become strange. This is one of the calmest and most important lessons of relativity. The travellers do not feel their own time slowing. Their hearts beat normally by their own measure. Their thoughts unfold normally by their own measure. Their clocks, if built well and protected from disturbance, continue to mark seconds in the usual way inside the ship. The change appears only when that ship is compared with another frame that moves differently, such as the frame of Earth or the frame of a distant destination. This effect is called time dilation, meaning that the elapsed time measured for the moving traveller is smaller than the elapsed time measured by a more stationary observer watching that traveller pass. The wording may seem dry, but the physical meaning is profound. If a ship travels at a very high fraction of the speed of light and later returns or sends back a precise comparison of clocks, less time passes for those aboard than for those who remain behind in a different inertial frame for most of the journey. The traveller does not notice any local slowing while it happens. The difference appears only in comparison, when the two histories are brought together and measured against one another. The simplest way to understand this is to let go of the old idea that time flows identically for all observers everywhere. In ordinary life, people share clocks closely enough that a single common time seems natural. A meeting begins at one moment for everyone in the room. A sunrise is marked on a schedule. A train departs according to a station clock. These experiences belong to a slow world, where differences caused by motion are too small to notice without careful instruments. Relativity shows that this common time is not universal. Each world line, meaning the path an object traces through space-time, carries its own elapsed time. A clock measures the time along its own path. If two clocks follow different paths through space-time, they need not accumulate the same amount of time between the same broad events. This does not make clocks unreliable. It makes them faithful to the structure of space-time. A clock aboard the ship is not malfunctioning when it shows less elapsed time than a clock on Earth after a relativistic voyage. It is reporting its own history exactly as relativity says it should. The difference is no more mysterious than two travellers reaching the same city by roads of different lengths and finding that one has walked fewer steps. In space-time, different motions carve different paths, and those paths contain different amounts of proper time, which is the time measured by a clock moving with the traveller. Once this idea is accepted, the effect becomes less like a paradox and more like a geometric fact. At moderate speeds, the difference remains tiny. Modern technology already measures it. Precise clocks carried on aircraft or placed aboard satellites do not remain perfectly synchronized with clocks on the ground unless relativistic effects are taken into account. Global navigation systems depend on such corrections. In those cases, the changes are small, but they are real and experimentally confirmed. As speed rises toward the speed of light, the same effect grows larger. The ship's clock continues with perfect normality in its own environment, yet compared with Earth, it marks a smaller passage of time over the same broad mission span. A journey that lasts years outside the ship may last much less for those inside, depending on the velocity and on the details of acceleration and deceleration. For the travellers, this means that time does not feel compressed. The shortening occurs in the comparison with the outside world, not in immediate experience. Meals are still eaten one after another. Sleep still follows waking. Tasks still require effort and duration. Memory still forms in sequence. Aging still proceeds according to the body's own biological processes as measured aboard. A person on such a voyage does not feel suspended outside time. The person simply carries a shorter interval of time between departure and arrival than those who remain behind in a different frame. The ship becomes, in effect, a moving pocket of ordinary lived duration set against a larger outside span. This creates one of the most striking consequences of relativistic travel. A sufficiently fast journey may carry people across immense cosmic distances while sparing them the full outside duration that such distances suggest. From the traveller's viewpoint, the mission may fit within a human lifetime more easily than it would from the viewpoint of those who stay behind. Yet the same fact also separates the traveller from the society left at home. The ship may return to find that many more years have passed on Earth than on board. Friends may have aged far more. Institutions may have changed. Languages, customs, and priorities may have shifted. The clock effect is therefore not only a matter of physics, it is a quiet reshaping of human continuity. The famous twin scenario expresses this clearly, though it is often simplified too much. The crucial point is not that each twin merely sees the other moving. The crucial point is that the travelling twin changes frames during departure, turnaround, and return, while the earthbound twin remains approximately in one inertial frame for most of the story. Their paths through space-time are not equivalent. When they meet again, relativity predicts a real age difference. This is not a contradiction inside the theory. It is one of the clearest ways the theory reveals that elapsed time belongs to actual paths, not to a single universal river flowing alike for all. In the calm interior of the spacecraft, clocks therefore gain a deeper meaning. They are not just tools for scheduling meals, shifts, and maintenance cycles. They are witnesses to the ship's route through space-time. Every tick marks local time honestly, and every comparison with the outside world reveals how motion alters the accumulation of that time. As velocity rises, the gap between ship time and Earth time grows. The mechanism does not need mystery to be powerful. It needs only the fixed speed of light and the structure of relativity. Seen from this region of the subject, the journey moves inward from the mechanics of acceleration into the rhythm of existence itself. The spacecraft continues through vacuum under load, but inside it clocks keep their own account, faithful and calm. Time does not break, it divides according to motion. The travellers live normally within their moving frame, yet when their clocks are set beside clocks that remained elsewhere, a difference stands plainly on the dial. Less time has passed aboard. That is what a near light-speed journey truly does to time for a massive traveller. It does not stop time, and it does not distort inner awareness. It simply allows one path through space-time to contain fewer lived moments than another. Distance seems simple when the world moves slowly. A road between two towns appears to have one stable length. A room has walls separated by a fixed span. A planet lies a certain number of kilometers from its star at a given point in its orbit. In ordinary life, these distances feel objective and shared. Different observers may disagree slightly because of measurement error or poor instruments. But they do not expect the distance itself to change merely because one observer moves quickly past it. Relativity changes that expectation. Once motion approaches the speed of light, distance along the direction of travel no longer remains the same for all observers. This effect is called length contraction, meaning that a moving length measured along the line of motion is found to be shorter by an observer for whom that length is in motion. The effect does not apply in every direction. Width across the path does not contract in the same way. Height perpendicular to the motion does not contract in the same way. The change belongs specifically to the direction in which one frame moves relative to another. This matters because a journey through space is not concerned equally with every dimension. What matters most to a traveller is the distance ahead, the path between departure and destination. Relativity leaves sideways dimensions unchanged in this basic sense, yet it narrows the route forward when measured in the moving frame. The long road through space becomes shorter for the traveller than it appears to observers who remain behind. This is not an optical illusion in the ordinary sense. It is not caused by the delay of light reaching the eye, and it is not a trick of perspective like a distant mountain appearing small on the horizon. It is a consequence of how space and time are measured together in different inertial frames. To determine the length of a moving object or the distance between moving markers, an observer must decide which points count as the two ends at the same moment. Relativity changes the meaning of the same moment for observers in relative motion. Because simultaneity changes, measured length changes as well. The contraction of length is therefore linked deeply to the relativity of simultaneity, even if daily language describes it more simply as a shortening along the line of travel. For the journey under discussion, the practical meaning is calm and striking. Suppose Earth observers describe a destination as lying many light years away. In their frame, that distance is real and stable enough for navigation. If a spacecraft moves toward that destination at a very high fraction of the speed of light, the travellers do not need to wait through the full Earth-measured span in their own proper time. Part of the reason is the time behaviour already described, but another part lies here in the path itself. In the ship's frame, the distance ahead contracts. The destination is not reached because space is conquered in the old ordinary way. It is reached because the traveller's measured separation from that destination becomes smaller than the Earth frame assigns to it. This can sound like a contradiction at first. How can one frame say the star is far away, while another says it is nearer, and both still describe the same universe? The answer lies in the structure of measurement. Distance is not an isolated fact floating free of the observer's state of motion. Distance between separated points depends on the frame used to assign space and time coordinates. In slow life, this dependence is too small to notice, so people treat distance as universal. In relativistic motion, that simplification no longer survives. Each frame gives its own self-consistent account, and the accounts are connected by the rules of relativity. No contradiction appears because each measured distance belongs to its own frame, and because the associated measurements of time change in a matching way. Inside the spacecraft, this means the cosmos ahead can become compressed along the direction of motion. A journey that appears impossibly long from Earth may fit into a much shorter path from the traveller's viewpoint if the speed is close enough to light speed. The stars do not physically pile up into one another, and the universe does not collapse in any universal sense. The contraction belongs to the measured coordinate distance in the moving frame. It is a lawful feature of space-time description, not a literal crushing of matter into smaller bulk by brute force. A planet at the destination still has its own size. The star it orbits still has its own structure. What changes for the traveller is the separation that must be crossed along the route. The effect grows with speed. At low velocity, the contraction is so slight that it disappears into ordinary uncertainty. At much higher velocity, it becomes significant. Near the speed of light, it becomes dramatic. The forward distance through interstellar space may shrink by a large factor in the ship's frame. This is one reason relativity allows the possibility, at least in principle, that human travellers could reach distant regions of space within their own lifetimes if an extraordinary vehicle could sustain the needed acceleration and survive the many other dangers. The outside universe would still age by a larger amount during the mission, but aboard the craft the path itself would be shorter. This shortening does not give the traveller permission to ignore the cosmic speed limit. The ship still moves slower than light in every local sense. It does not leap across space instantly, and it does not break the structure of causality. The reduction of distance is not a loophole around relativity, but one of relativity's own consequences. The traveller covers a shorter measured interval in the ship's frame while remaining subluminal, meaning slower than light. The universe does not relax its rule. It simply links distance and time in a way that allows very fast travellers to inhabit a different geometry of the journey than slow observers do. There is a quiet human meaning in this as well. On Earth, remoteness often feels absolute. A distant star system appears separated by a gulf too vast for personal travel. Relativity softens that remoteness for the traveller, without softening it for those left behind. From the home frame, the gulf remains immense. From the ship frame, the gulf narrows. The same mission therefore carries two equally valid senses of distance. One belongs to the civilization watching the voyage from afar. The other belongs to the people inside the vessel, moving so quickly that the route itself shortens before them. Seen from this region of the subject, the inward journey through relativity now reaches the road ahead. Time aboard the craft follows its own rhythm, and distance ahead no longer keeps a single universal measure. The line from origin to destination contracts along the direction of motion, becoming shorter for the fast-moving traveller than for those at relative rest with respect to the starting world. The effect is not visual trickery, not instrument failure, and not speculative escape from known physics. It is part of the same disciplined structure that fixes the speed of light and reshapes space and time around that fact. A near light speed traveller therefore does not simply endure a long crossing more quickly. The traveller inhabits a shorter crossing altogether. Inside a fast-moving spacecraft, the outside universe does not merely remain what it is in the slower frame of Earth, and then present itself unchanged through the windows. Light carries the scene inward, and when the observer moves at a very high fraction of the speed of light, the arriving light no longer enters in the same way. The stars, the dark between them, the glow of distant dust, and the broad background of the cosmos are still there, but their appearance is altered by the motion of the ship. This region of the journey belongs not yet to impact or bodily strain, but to perception through light itself. The question is no longer how far the destination lies, or how the clocks compare. The question is what the universe looks like when its light reaches a traveller moving at relativistic speed. Light enters the ship from many directions. In ordinary experience, a person standing still on Earth or moving slowly in a vehicle sees little change in the overall arrangement of the sky, because the speed of the observer is tiny compared with the speed of light. The stars keep their familiar patterns. Their colours remain much the same to the eye. The brightness of the sky changes with the atmosphere, time of day, clouds, and local conditions. But motion alone makes little visible difference. Relativistic travel changes that quiet stability. Because the spacecraft moves so quickly, the direction from which light seems to arrive begins to shift. Light that once approached from a wide range of angles appears to crowd forward toward the direction of motion. This effect is called aberration. In plain terms, aberration means that incoming light seems to tilt toward the forward direction for a fast-moving observer. A useful everyday analogy exists in rain. When a person stands still in falling rain, the drops seem to fall mostly downward. When that person runs forward, the rain seems to slant toward the face. The rain itself has not changed in the same way that it would if a new wind suddenly arrived. What changes is the motion of the observer through the falling pattern. Relativistic aberration is more subtle and more exact, but the broad idea is similar. As the spacecraft moves faster, more and more of the visible sky appears compressed into a bright region ahead, while the region behind seems to spread and thin. The constellations therefore do not remain fixed in their familiar arrangement. They distort. Stars that are widely separated across the ordinary sky may appear drawn inward toward the ship's forward line of travel. The whole star field begins to gather into a smaller apparent patch in front of the craft. Behind the ship, the sky seems to open and stretch. This does not mean the stars physically move into new positions. It means the angles at which their light enters the moving frame have changed. The traveller therefore inhabits a sky reorganized by motion, a sky whose shape is no longer the slow sky known from planets and moons. Colour changes as well. Light is carried by waves, and when observer and source move relative to one another, the frequency of the incoming light changes. This is the Doppler effect, defined simply as the shift in frequency caused by relative motion. In sound, the effect is familiar in the changing pitch of a passing siren. With light, the change appears as a shift in colour or, more generally, a shift to different parts of the electromagnetic spectrum. Light from the forward direction is shifted toward shorter wavelengths. Visible red may move toward blue. infrared may move into visible light. Light arriving from behind is shifted toward longer wavelengths. Visible light may slide toward infrared and beyond. The traveller does not simply see the ordinary universe gathered forward. The traveller sees it recoloured by motion, at moderate relativistic speed. These shifts might be noticeable but limited. At more extreme speed, they become severe. A star that looks warm and reddish in a slower frame may appear whiter or bluer when seen nearly head-on by the ship. A dark region ahead may brighten if light that was once outside human vision is shifted into the visible range. Meanwhile, the sky behind may lose visible brightness as familiar starlight slides out of the visible band. The universe becomes uneven in its presentation. Forward space grows optically richer and more intense, while rearward space may become dimmer and less populated to human sight. Brightness is altered not only by colour shift but by concentration. Because aberration packs more of the visible sky into the forward direction, light there becomes more focused. The result is often called relativistic beaming. In simple language, the forward field of view grows brighter because more incoming light is gathered into a smaller apparent region, and because that light is also shifted upward in frequency. The effect does not create energy from nothing. It changes how existing incoming radiation is distributed across the traveller's sky. The forward universe may therefore appear compressed, sharpened, and intensified, while the rearward universe becomes diluted and subdued. This means the ship's windows, sensors, and optical systems would not offer a calm ordinary panorama. A forward-facing view would become increasingly dominated by a narrowed cone of light and structure. The side view would lose some of its former breadth. The rearward view would fade in both colour and angular richness. A navigator relying on ordinary human expectations of the night sky would find them no longer trustworthy. Instruments would need to account for the new geometry of arrival, separating true source properties from the distortions produced by the ship's motion. Even the apparent blackness between stars would change character. Some regions ahead that seemed dark in the slower frame might become more luminous if radiation shifted into visible wavelengths. Some familiar stars behind the craft might seem to vanish from sight, not because they cease to exist, but because their light has moved beyond the sensitivity of the eye. The ship would therefore travel through a universe that is still physically the same in its broad external structure, yet optically transformed by the conditions of observation. Motion rewrites appearance without rewriting the objects themselves. Seen from this region of the subject, light entering the cabin becomes a messenger reshaped by speed. The sky ahead contracts toward the line of travel. The stars distort toward the front. Colours shift, with forward light moving toward shorter wavelengths and rearward light toward longer ones. Brightness gathers unequally, making the universe seem concentrated in front and thinned behind. None of this requires speculation. It follows from the same relativistic framework that changes time and distance. A near-light-speed traveller therefore does not look out on the ordinary heavens from an unusually fast seat. The traveller looks out on a sky whose light has been redirected, recoloured, and redistributed by motion itself. Light is often imagined as the gentle part of the journey. It reveals stars, outlines planets, and gives the traveller a view of the universe beyond the hull. Yet light is not gentle by nature in every form. Visible light is only a small middle band within the full electromagnetic spectrum. Beyond it lie infrared, ultraviolet, X-rays, and gamma rays. These are not different substances. They are the same kind of radiation differing in wavelength, frequency, and energy. As wavelength becomes shorter, frequency becomes higher, and the energy carried by each photon rises. This quiet ordering of the spectrum becomes important at extreme speed, because motion can shift incoming light upward along that ladder of energy. The shift has already appeared in the previous region as a change of colour. Here the concern deepens. A forward blue shift does not stop at making reddish light seem bluish. If the relative motion is high enough, light that begins as visible may be shifted into ultraviolet. Light that begins as ultraviolet may be shifted into X-rays. Still greater shifts push radiation toward gamma rays. Space. Com notes that blue shift is the increase in light frequency when the source and observer move toward one another, and that the terms apply across the whole electromagnetic spectrum, not only to visible colour. In ordinary astronomy, this is often a tool for measurement. In near light speed travel, it becomes a question of exposure. This matters because high-energy radiation interacts with matter differently from ordinary visible light. NASA explains that gamma rays, X-rays, and some ultraviolet radiation are ionizing, meaning they carry enough energy to remove electrons from atoms. When atoms and molecules are altered in this way, biological tissue can be damaged. The danger does not arise because the universe becomes hostile in a new magical sense. It arises because the craft's speed changes the form in which ordinary incoming radiation is received. A beam that would have illuminated the hull softly at lower speed may arrive at much higher energy when the ship rushes into it fast enough. Motion turns illumination into a more penetrating encounter. The forward direction is the crucial one. Relativistic aberration already narrows incoming light into a cone ahead of the ship, and relativistic beaming concentrates brightness there. The Doppler effect then shifts that concentrated forward light to higher frequency. These effects act together. More light is packed into the front of the traveller's sky, and that light is shifted toward greater energy. What begins as a visual transformation in Section 9 becomes a radiation problem in Section 10. The ship is not only seeing a brighter and bluer forward universe, it is receiving a front-loaded increase in energetic photons. The consequence is not simply glare, it is exposure to a harsher part of the spectrum. On Earth, living things are protected from much of this hazard by the atmosphere. NASA notes that the atmosphere blocks a range of high-energy waves that would otherwise reach the surface in far greater quantity. A relativistic spacecraft in deep space carries no such planetary blanket around it. The hull, windows, sensors, and shielding systems stand directly between the crew and incoming radiation. This does not mean every near-light-speed voyage is instantly lethal from starlight alone. The severity depends on velocity, direction, and the spectral character of the radiation field ahead. Still, the broad physical rule is clear. As speed rises, the incoming photon environment becomes progressively harder, especially in the forward direction. Even light that begins outside human sight may become newly important. Infrared radiation from stars, warm dust, or other diffuse sources may be shifted into visible or ultraviolet bands. Radiation already in the ultraviolet may be shifted upward into X-rays. NASA's spectrum material makes clear that the electromagnetic spectrum is continuous, extending from long-wave radio to very short gamma rays. That continuity means there is no protective boundary in the radiation itself where one kind of wave politely ends and another begins. There's only gradual increase in frequency and energy. At sufficiently high relative speed, the ship receives the forward universe translated into a more energetic language. The traveller enters not a different cosmos, but a transformed spectrum. Sensors and windows become part of the problem. Materials that are transparent to visible light are not automatically safe against intense ultraviolet or X-ray exposure. Instruments designed for ordinary navigation may be overwhelmed or require heavy filtering. Observation ports that seem simple in a slow spacecraft become less simple when the forward field is both concentrated and hardened by motion. Even if the crew rarely looks directly outward, the ship still has to measure the space ahead, and measurement means interaction with incoming radiation. A near-light-speed craft would therefore need to treat the forward view not as a scenic opening but as a managed radiation interface, carefully monitored and heavily engineered. There is also an important difference between apparent colour and actual hazard. Human vision may register only a narrow portion of the change spectrum. A sky that appears merely brighter or more bluish could conceal a much larger rise in ultraviolet or X-ray flux outside the eye's detection. NASA emphasizes that visible light occupies only a small central region of the electromagnetic spectrum, and that instruments are needed for the rest. A crew relying on eyesight alone would miss much of the energetic transformation. The most dangerous part of the incoming radiation may therefore be invisible. The danger belongs to photon energy and biological interaction, not to appearance alone. The underlying physics remains calm even when the implication is severe. Nothing supernatural occurs. The ship does not create new radiation from nowhere. It changes the measured frequency and distribution of radiation already present in the environment because of its own motion. This is the same Doppler principle used throughout astronomy, carried into a more extreme regime: space. COM describes blue shift as the rise in frequency when approach compresses the waves. NASA explains that shorter wavelengths correspond to higher energy, and that the highest energy bands are capable of ionization and damage, joined together. These facts explain why forward light at relativistic speed becomes not only visually altered, but physically dangerous. Seen from this region of the subject, the universe ahead is no longer a passive source of scenery. Its light arrives compressed, concentrated, and shifted up the electromagnetic spectrum. Visible light may become ultraviolet, ultraviolet may become X-rays, and the incoming radiation field can grow increasingly ionizing as speed rises. Earth's atmosphere normally softens such exposure, but a deep space craft must face it directly with its own materials and systems. The traveller therefore learns that approaching light speed does more than reshape time, distance, and the appearance of the stars. It changes the very character of incoming light, turning what seems like illumination into a forward-streaming radiation hazard carried by the same photons that once only lit the way. Interstellar space looks empty, but the route ahead is not truly blank. NASA describes the interstellar medium as the space between stars sprinkled with gas and dust, and ESA similarly describes the local interstellar cloud as an almost empty bubble of gas and dust, through which the solar system moves. That wording matters. Almost empty is not the same as empty. For an ordinary spacecraft moving at modest speed, this sparse material is usually too thin to resemble weather or drag in the earthly sense. For a spacecraft moving at a very high fraction of the speed of light, the same material ceases to be negligible. It becomes the oncoming substance of the journey, striking the front of the vehicle as a continuous stream of atoms and an occasional but far more dangerous population of dust grains. The change comes from relative speed. A single atom of hydrogen drifting quietly through the interstellar medium does not seem threatening when considered in its own calm environment. Yet when a fast ship rushes into that atom, the encounter is no longer gentle. The ship meets not a gas in the everyday sense, but a beam of incoming particles concentrated on its forward surfaces. One scientific review of relativistic flight describes interstellar gas and cosmic rays as a severe radiation hazard for a relativistic interstellar ship, and notes that the oncoming flow of interstellar gas produces especially intense exposure. Another study on relativistic spacecraft identifies damage from interstellar gas and dust as a critical challenge for such missions. The thin medium remains thin, but speed magnifies the significance of every impact. Present-day spacecraft already show how much velocity matters. NASA's micrometeoroid and orbital debris guidance explains that tiny particles moving at hypervelocity can cause serious damage or catastrophic failure, and gives examples in which even very small debris can strike with destructive effect. NASA Ames material on meteoroid impacts adds that meteoroids entering at speeds up to 72 km per second can ionize and vaporize themselves and a significant portion of the spacecraft material upon impact, producing an expanding plasma. These are speeds vastly below relativistic travel, yet they already force engineers to treat tiny particles as major threats. The lesson scales in a clear direction. If grains and atoms are dangerous at tens of kilometers per second, they become much more serious when the closing speed rises by orders of magnitude. Gas and dust do not threaten in the same way. Gas atoms are far smaller and far more numerous. Dust grains are far rarer, but each one carries far more mass than a single atom and therefore can deliver far more damage in a single collision. Studies of relativistic spacecraft therefore separate the two hazards. Gas bombardment acts as a relentless spray across the forward face of the vehicle, contributing cumulative damage, heating, ionization, and material change. Dust behaves more like sporadic high-energy strikes. An assessment of interstellar dust impacts notes that spacecraft traveling to nearby stars will experience energetic collisions with interstellar dust grains, and that for thick structures all the grain energy may be deposited, leading to significant damage. The voyage, therefore, faces both a constant abrasive stream and a punctuating threat from larger particles. For the hull, a gas impact at extreme speed is not best imagined as a breeze. It is closer in physical consequence to bombardment. Forward-facing material meets a continuous rain of nuclei and electrons carrying very high relative energy. Over time, this can erode surfaces, alter coatings, damage electronics, and burden any exposed sensor. A related study on relativistic interstellar spacecraft summarizes dust bombardment as a source of erosion and crater formation caused by explosive evaporation of surface atoms. Although that description focuses on dust, it helps clarify the larger principle. At sufficient impact energy, matter does not simply bounce or dent, it may vaporize, ionize, sputter away, or send fragments deeper into the structure. The front of the craft becomes a working surface under microscopic attack. Dust grains intensify the danger because each strike is localized and violent. Space agencies already test shielding against hypervelocity projectiles because small impacts can pierce protective layers and damage vital systems. ESA hypervelocity testing shows millimeter-scale projectiles punching through candidate spacecraft shielding at speeds around 7 km per second, while NASA materials on impact plasma show that high-speed meteoroids can create ionized vapor plumes. At relativistic travel speeds, an interstellar dust grain would not be a nuisance particle. It would behave like a compact delivery of enormous kinetic energy into a tiny area. The likely result is not merely a surface scratch, it is crater excavation, localized melting or vaporization, ejecta thrown into nearby structures, and in some cases secondary damage deeper inside the vehicle. Another consequence follows from the plasma created in violent impacts. NASA Ames notes that impact-generated plasma can expand into the surrounding vacuum, and ESA reporting on Mars Express explains that if an impact punctures into a spacecraft, the plasma produced can provide an electrical connection from the charged outer body to internal components. This turns a physical strike into an electrical hazard as well. A near-light-speed craft would therefore face more than erosion and cratering. Each sufficiently energetic collision could also generate charged material, electromagnetic disturbance, and secondary failure in instruments or power systems. The danger spreads from the point of contact into the wider electrical life of the ship. A tiny grain may arrive at one location and leave consequences in several systems at once. Seen from this region of the subject, the quiet vacuum around a relativistic spacecraft is no longer truly quiet. It contains gas and dust, thinly distributed but physically real, and the ship meets them at extraordinary closing speed. Atoms become a relentless forward bombardment. Dust grains become rare but potentially devastating impacts. Both derive their danger not from large size but from the energy of relative motion. What seems almost nothing in a slow frame becomes a serious medium of collision in a fast one. The traveller therefore learns that the emptiness between stars is not a harmless corridor. It is a sparse environment that turns hostile when crossed too quickly, because every particle ahead becomes an encounter with matter delivered at extreme energy. Once collisions with gas and dust become energetic enough, the problem is no longer only that matter strikes the ship. The problem is that the struck material changes state. Hypervelocity impacts do not behave like ordinary dents made by stones or metal fragments in slow air. ESA explains that beyond sufficiently high impact velocity, a projectile can break up completely and melt, while crater material is ejected from the target as shock waves move through it. NASA Ames describes meteoroid impacts as energetic enough to ionize and vaporize both the particle and a significant portion of the spacecraft material, forming a plasma that rapidly expands into the surrounding vacuum. In plain terms, the front of a fast ship does not merely absorb impacts. It experiences localized events of heating, fragmentation, melting, vaporization, and electrically active plasma formation. Heat in this region of the journey is therefore produced in two linked ways. One source is the ship's own machinery, which already creates waste heat during power generation, propulsion, and life support. NASA's thermal control guidance notes that spacecraft temperature depends on how much heat is absorbed, stored, generated, and dissipated, while ESI describes thermal control as essential because equipment can be damaged or degraded if temperatures leave their allowed range. The second source is the outside environment at extreme speed. Incoming particles and radiation deposit energy into the forward structure, and impact events convert kinetic energy into internal energy inside the shield. The ship must therefore manage both internal heat and collision-driven heating at the same time, in vacuum. Where there is no surrounding air to carry heat away by convection, that burden is especially serious. A shielding system for such a craft cannot be a single idea serving one threat. It must answer several different physical problems at once. It must reduce puncture risk from dust and debris. It must absorb or spread the energy of impacts. It must limit the radiation dose reaching crew and electronics. It must cope with plasma and electrically disturbed material near the impact site. It must also avoid becoming so heavy that the ship can no longer be accelerated economically. NASA's Hypervelocity Impact Technology Group states plainly that spacecraft shield designers must develop solutions that are effective while staying within mass, volume, and cost limits. This is the quiet central tension of shielding. More protection usually means more mass, but more mass makes every earlier problem of acceleration and energy worse. One mature answer to high-speed particle impact is the Whipple shield. NASA describes it as a sacrificial bumper placed in front of the spacecraft so that the first layer takes the initial strike. The bumper shocks the projectile and turns it into a debris cloud of smaller fragments that spread over a larger area before reaching the rear wall. ESA gives the same basic description. Adding the intermediate fabric layers can further slow the cloud particles, and that such shields have reached a mature state of development for present spacecraft protection. This principle matters because stopping a compact impactor directly in one thick wall is often less efficient than first breaking it apart and then dealing with the diluted spray. The shield does not try to make the projectile remain whole. It tries to destroy its concentrated form before that form can penetrate inward. NASA also describes a stuffed Whipple shield, in which layers such as Nextel and Kevlar are inserted between bumper and rear wall, so that the debris cloud is further shocked and pulverized before it reaches the pressure boundary. More recent NASA test work reports that hydrogen-rich polymer materials in intermediate and final layers improve both meteoroid and debris protection and radiation protection. That dual function is important. A relativistic craft does not face a clean separation between mechanical impact and radiation hazard. The same forward structure must answer both. A good shield is therefore not only a wall, it is a sequence of materials arranged so that each layer changes the threat into a form that the next layer can better handle. Radiation adds a second design rule. NASA's radiation shielding guidance says that low atomic number materials such as liquid hydrogen, water, and polyethylene provide the best protection against most space radiations, and that the internal radiation environment depends on how the external environment is modified as particles pass through spacecraft material. That last point is especially important. A shield does not simply block radiation in an all-or-nothing sense. It transforms the incoming environment. Some particles are absorbed, some are slowed, some produce secondary radiation inside the shielding itself. For a very fast ship, studies of relativistic flight note that neutral particles in the interstellar medium limit the usefulness of magnetic or electrostatic shielding alone, making some form of forward material shielding necessary, while also warning that secondary showers can arise in thick shields. The protective barrier must therefore be designed not merely to stop what comes in, but to control what new hazards are created inside the barrier. Plasma complicates the picture further. NASA Ames reports that impact-generated plasma can expand rapidly in vacuum, and that the associated electrical effects may threaten spacecraft electronics, with local electromagnetic fields near the impact site potentially exceeding current spacecraft design specifications. In a slow spacecraft, this is already an engineering concern. In a much faster one, where each forward impact carries more energy, plasma is not just a byproduct. It becomes part of the threat environment immediately in front of and around the shield. The protection system must therefore include electrical hardening as well as mechanical strength. Sensitive electronics may need distance from the bow. Conductive pathways may need careful design, and impact-exposed regions may need to be treated as zones of repeated transient electrical disturbance rather than simple metal surfaces. Thermal control now returns as a full systems problem. ESA describes thermal control as necessary to keep temperatures within set limits for the life of a space system, and NASA notes that spacecraft heat must be dissipated as well as absorbed and stored. A heavily shielded bow that absorbs repeated impact energy and intense forward radiation cannot simply keep warming without consequence. Heat must travel from exposed surfaces into thermal pathways and then be rejected, mainly by radiators. Yet radiators themselves are vulnerable structures, and added thermal hardware adds mass. Some present-day spacecraft already combine protective and thermal functions in outer layers, as NASA's shielding work notes in the use of body-mounted radiators as initial shield layers in some designs. For a relativistic craft, this suggests a broader design philosophy in which shielding, thermal rejection, and structural layout cannot be separated into isolated departments. They become one integrated forward defense system. The likely result is a ship with a strongly protected front and a deliberately organized interior behind it. The forward direction, sometimes called the RAM direction in spacecraft engineering, would demand the greatest shielding because that is where incoming particles, radiation, and impact plasma are concentrated. NASA's recent shielding paper notes that the International Space Station uses stuffed Whipple shielding on directions where the greatest impact rates are expected. A relativistic ship would take the same principle much further. Not every side of the craft faces equal danger. The bow becomes the working edge that sacrifices material, spreads shocks, reshapes particle clouds, absorbs radiation, and protects the more delicate interior systems behind it. Seen from this region of the subject, survival at extreme speed depends less on one miraculous material than on layered compromise. Impacts create heat. Heat and shock create melting, vapor, and plasma. Radiation hardens as velocity rises. Shields must fragment incoming particles, slow debris clouds, absorb or moderate radiation, limit secondary effects, and then shed the waste heat that remains. All of this must happen without turning the craft into an unlaunchable mass. The near-light-speed ship therefore carries its safety not in a simple thick shell, but in a carefully staged frontier of bumpers, fabrics, hydrogen-rich matter, electrical protection, and thermal control. The space ahead remains sparse, but the ship meets it so violently that protection becomes an entire architecture of transformation between the violent exterior and the habitable world within. Inside a relativistic spacecraft, the human body remains what it has always been on Earth, a soft, water-rich, electrically active, biologically timed organism with narrow limits. Bones require loading, muscles require use, blood requires stable circulation, the brain requires oxygen and sleep, and tissue depends on protection from ionizing radiation. The ship may be built from metals, composites, sensors, and shielding, but the crew is built from cells. That simple contrast governs life inside the vessel. A machine may endure conditions that a person cannot. Any serious journey toward light speed therefore becomes, at its core, a problem of keeping fragile biology functioning inside an extreme mechanical and radiative environment. The first bodily question is gravity or its absence. NASA's human research material treats altered gravity fields as one of the major hazards of spaceflight, and long-duration microgravity is known to contribute to bone loss, muscle loss, and cardiovascular and sensoromotor deconditioning. At the same time, NASA artificial gravity work notes that replacing terrestrial loading with centrifugation or sustained linear acceleration is widely regarded as the most effective physiological countermeasure, because many spaceflight changes stem from the loss of ordinary gravitational loading for a relativistic ship. This suggests that if the craft could sustain something close to Earth-like loading through steady acceleration, some classic harms of weightlessness would likely be reduced. Even so, the long-duration human evidence base for years of sustained linear acceleration remains limited, so the exact bodily outcome cannot be stated with confidence. Radiation remains the quieter and less forgiving threat. NASA's Human Research Program identifies space radiation as one of the central hazards of exploration missions, and current NASA material states that exposure can increase risks such as cancer, cardiovascular disease, and damage to the central nervous system. NASA also notes that some particles, especially galactic cosmic rays, are difficult to shield against fully inside a relativistic craft. This concern does not disappear merely because the crew is enclosed. The crew lives behind shielding, but no practical shield turns deep space radiation into complete safety. And the forward hardening of the radiation environment at very high speed makes the burden more severe. The medical meaning of this exposure is both immediate and long-term. High acute doses can produce sickness and impair function, while lower accumulated doses are associated with delayed disease risk. NASA evidence reports describe risks of radiation carcinogenesis, and also ongoing concern about central nervous system and cardiovascular effects. For a crew on an extended journey, this means health cannot be judged only by how the astronauts feel on a given day. A person may appear operational while biological injury accumulates silently. Monitoring would need to be continuous, and the ship's medical logic would have to assume that prevention is more valuable than treatment, because many radiation effects cannot be simply reversed once established. Confinement changes the body and mind in a different way. NASA's isolation and confinement material asks directly how such conditions affect behavioral health and performance for individuals and teams, while NASA risk descriptions note that prolonged isolation may lead to inadequate functioning within a crew and that communication delays can worsen stress, cohesion, and coordination. A relativistic vessel is socially closed. The same people, the same walls, the same air systems, and the same narrow routines remain present day after day. Privacy becomes more important as missions lengthen, and so do predictability, trust, and the fair distribution of labor, appetite, immunity, mood, stress hormones, and decision-making all respond to the social environment in which life is sustained. Sleep and circadian timing make this even more delicate. NASA evidence reports state that astronauts experience sleep loss, circadian desynchronization, and work overload during spaceflight, and that these conditions can reduce performance and contribute to adverse health outcomes. NASA's more recent work on sleep aboard the International Space Station reports that scheduled sleep was circadian misaligned in roughly 1 out of every 5 sleep episodes, and that those misaligned episodes were associated with nearly 1 hour less sleep and poorer reported quality. A relativistic crew would still live one day after another inside the ship, but the body clock would need careful protection through lighting, routine, noise control, and work scheduling. Without that protection, cognition may dull, reaction time may slow, judgment may weaken, and emotional strain may deepen even if the spacecraft itself remains technically sound. Distance from Earth also changes medicine. NASA's 5 hazards framework treats distance from Earth as a distinct exploration hazard because evacuation, resupply, and immediate ground support become less available. On a deep voyage, the crew must become more medically autonomous. Small illness, minor injury, infection, vision change, or medication shortage can no longer be handled as inconveniences to be solved quickly from home. The human body still ages, heals, inflames, tires, and occasionally fails. A long relativistic mission would therefore require the ship not only to shield the body from extreme hazards, but also to sustain routine health across years of enclosed living with limited outside assistance. There is also a quiet psychological burden in the mismatch between live time aboard and elapsed time elsewhere. Relativity may allow the travellers to age less than people left behind, but their minds still experience a continuous personal duration filled with work, memory, attachment, and expectation. NASA's behavioral health material emphasizes the risks of stress, reduced well-being, and psychiatric or behavioral changes under extreme space stresses. For a crew that knows the outside world is advancing on a different clock, separation is not only spatial, it becomes historical. Family members, institutions, and societies at home may move farther away in time even while the crew preserves a more compact personal interval. What remains uncertain is substantial. NASA's recent risk evaluation work notes that the evidence base is limited because fewer than 700 humans have ever flown in space, and much of what is known comes from low Earth orbit missions, terrestrial analogues, and extrapolation. That limitation matters here. No one has lived for years in a relativistic spacecraft under sustained linear acceleration, chronic deep space radiation, extreme communication delay, and the social closure of interstellar travel. The best current science can identify the major hazards with confidence, but it cannot map every combined effect in detail. Seen from this region of the subject, the human body inside a near-light-speed craft is not a passive passenger. It is the mission's most delicate system, requiring gravity or its substitute, radiation protection, sleep discipline, social stability, medical autonomy, and constant care. Inside the ship, experience remains local. A clock on the wall ticks with its own steady rhythm. Meals arrive in sequence. Sleep follows waking, and work occupies blocks of attention that feel ordinary from within. Special relativity does not cause a traveller to feel time slowing in a direct bodily sense. Einstein Online explains that from the point of view of an inertial observer, a moving clock goes slower than an identically built clock at rest, and that all processes moving with that clock are slowed in the same fashion. This means that everything aboard the ship, including thought, gesture, metabolism, and memory, unfolds normally by the ship's own measure. The traveller does not sense a missing fraction of a second. The difference appears only when the ship's history is compared with a different history elsewhere. This gives the voyage a peculiar calm. The crew lives inside a complete little world whose internal order remains intact. Nothing in ordinary perception tells them that Earth time and ship time are separating. A diary entry written at the end of a shift still feels one shift away from the entry before it. A task that takes an hour still takes an hour by the ship's clocks. The strange part of relativistic experience is therefore not that consciousness becomes blurred or stretched. It is that the outside comparison changes while the inside flow remains coherent. The traveller experiences continuity, while physics later reveals divergence. The idea of a shared present also begins to loosen. Einstein Online notes that simultaneity is not something simply given, but something that must be defined, and that in special relativity which events count as simultaneous depends on the chosen frame of reference. For the traveller, this means that the word now no longer has one universal meaning extending cleanly from the cabin to Earth and onward across the stars. The crew may keep a shipboard date and hour, and Earth may keep another, but the deeper relativistic lesson is that there is no single cosmic moment against which all distant events are stamped at once. Experience inside the ship remains ordered, yet the idea of a common outside present becomes harder to hold. Communication makes this abstraction tangible. NASA states that for Mars, missions communication delays can reach up to 20 minutes one way. and NASA technical work on crew autonomy explains that increasing one-way light time delays reduce the possibility of real-time support from mission control and require crews to function more independently. A relativistic voyage extends the same principle into a much deeper register. Messages still travel at light speed, not at the speed of wish or urgency. The traveller therefore experiences Earth not as a continuously present partner, but as a delayed correspondent. Advice arrives after waiting. Questions return after more waiting. Even if the emotional bond remains strong, conversation ceases to feel immediate and begins to resemble exchange across a widening historical interval. The view outward changes the inner experience as much as the delayed messages do. Einstein. Online's treatment of the Doppler effect and NASA's descriptions of the electromagnetic spectrum together support the same broad picture motion shifts incoming light in frequency, and high relative speed changes how the outside world is presented to the moving observer. Earlier sections describe the physics of aberration, blue shift, and beaming. In lived terms, these effects mean that the traveller no longer inhabits a familiar night sky. The heavens ahead gather toward the forward direction. Brightness concentrates, and the visual field loses the quiet evenness known from a planet's surface. Outside the cabin, the universe looks less like a dome of distant lamps and more like a scene reorganized by the ship's motion. This unfamiliar sky has psychological weight. NASA notes that spacecraft windows can reduce monotony and the sense of confinement, and can therefore support mental health during spaceflight. At relativistic speed, a window still performs that human function, but what it reveals is less comforting in the old terrestrial sense. It offers contact with reality beyond the hull, yet that reality appears optically transformed. The traveller may gain relief from enclosure by looking outward, while also confronting a universe that no longer looks stable or intuitively arranged. The window becomes both solace and lesson. It helps preserve mental balance even as it reminds the crew that they occupy a frame of motion very different from the worlds they left behind. Routine becomes the main instrument by which perception is stabilized. NASA's human spaceflight guidance emphasizes the importance of habitability, sleep discipline, and psychological support in closed missions. A NASA behavioral health material links isolation and confinement with effects on sleep, morale, and decision-making. For the traveller, routine does more than preserve health. It preserves a sense of ordinary reality. Artificial lighting marks morning and evening. Scheduled work separates effort from rest. Meals, exercise, and maintenance prevent consciousness from dissolving into an endless, undifferentiated duration. In a voyage where external time relations become strange, internal routine becomes the structure by which experience remains humane and intelligible. Privacy matters for the same reason. NASA notes that privacy is a top priority for a crew's psychological well-being in confined deep space settings. A relativistic ship may present grand scientific strangeness outside, but inside it still asks people to live near one another for long periods in limited volume. The conscious experience of the mission therefore depends not only on equations and clocks, but on whether a person can withdraw, think quietly, sleep without constant interruption, and maintain some protected inner life. Without such spaces, the unusual physics of the voyage would be filtered through exhaustion and friction. With them, the traveller is better able to meet the altered universe with steadier attention. The traveller's understanding of distance also changes from a felt abstraction into a lived contradiction. Communication delay makes Earth feel farther away in one sense, while relativistic shortening of the route makes the destination feel nearer in another. Time aboard remains ordinary, yet the outside world advances by a different measure. Einstein. Online's discussions of time dilation and simultaneity make clear that these are not conflicting fantasies but lawful features of different frames. In consciousness, however, they may coexist uneasily. Home recedes in immediacy, even as the path ahead grows shorter in the ship's account. The voyage therefore acquires a dual character. It is intimate in local time and estranging in relation to the wider universe. Seen from this region of the subject, the true human experience of near light-speed travel is not a blur of cinematic distortion. It is a disciplined, ordinary life carried through extraordinary physical relations. The traveller feels normal time locally, yet later finds that less time has passed aboard than elsewhere. The traveller looks out through windows that ease confinement, yet those windows reveal a sky reshaped by motion. Messages from Earth still arrive, yet never with perfect immediacy, and the idea of a universal shared present quietly falls away. What remains is a life lived in a self-consistent moving world, where perception stays coherent inside the ship even as the surrounding universe is measured, seen, and understood in a radically unfamiliar way. At the innermost point of this subject, the question becomes simple again. What would really happen if a human-made spacecraft tried to reach the speed of light? The answer given by modern physics is calm and exact. A spacecraft made of ordinary matter would not reach it. It could accelerate toward it, perhaps very closely in principle, but it would never arrive at the exact boundary. The true outcome is not a final crossing into some new state of travel. The true outcome is an endless approach, in which the familiar effects of relativity grow stronger, while the last step remains forbidden. This limit does not appear as a wall hanging in space. No bright barrier waits ahead of the bow. No physical line is painted across the universe. Instead, the limit is built into the relationship between mass, energy, space, and time. Earlier sections have shown its signs from many angles. The energy cost rises more and more steeply. Time aboard the craft passes more slowly relative to distant observers. Distance along the route contracts in the ship's frame. Light ahead becomes concentrated and shifted toward higher energy. Radiation hardens. The sparse medium of space becomes a sort of impact hazard. Each of these changes is not a separate obstacle invented by a different branch of science. They are expressions of one coherent structure. The closer a massive traveller comes to light speed, the more clearly that structure reveals itself. A massless thing such as a photon lives naturally at this boundary. It does not need to be accelerated up from rest in the ordinary sense, because it has no rest frame like a massive object. Matter does not share that condition. A spacecraft, a body, a dust grain, or a planet carries mass, and mass keeps it on the slower side of the divide. The ship may be pushed, fed with energy, and driven across enormous distance, but every added gain in speed confirms the same rule. The craft can continue to approach the limit without ever becoming light-like. That word, light-like, simply means following the kind of space-time path that light itself follows. Matter does not cross into that kind of path through ordinary acceleration. What really happens instead is more subtle and, in some ways, more remarkable than the old dream of simply matching light. The spacecraft enters a regime where outside years and inside years separate sharply. For those aboard, distant journeys may become shorter in lived duration than they appear from the home world. The route ahead may shrink in the ship's frame. The stars may compress toward the forward direction. The travellers may cross spans that once seemed hopelessly remote. Yet all of this occurs while remaining below light speed. Relativity does not grant victory over the cosmic limit. It grants a different way of inhabiting motion near that limit, one in which time and distance are rebalanced without the final boundary ever being broken. This is why the deepest truth of the subject is not disappointment, but correction. Many people first meet the idea of light speed through a simple image of racing faster and faster until one finally arrives at the highest number nature allows. Modern physics replaces that image with a more disciplined one. Speed near the cosmic limit is not a ladder with a last rung waiting to be stepped on. It is a narrowing region in which each additional gain demands far more than the one before. A journey into that region becomes dominated by cost, shielding, heat, impact hazard, and human fragility. The ship may still move astonishingly fast by human standards. It may still transform the relation between traveller and cosmos, but it never becomes a beam of light, and it never escapes the price imposed by mass. This also explains why faster-than-light travel remains outside established physics. If even reaching light speed is impossible for massive matter through ordinary motion, then exceeding it does not arise as the next natural engineering milestone. It would require a deeper revision of known theory or some entirely different physical mechanism, none of which has been demonstrated in a practical or experimentally confirmed form for travel by macroscopic objects. Serious physics allows speculative ideas to be discussed, but speculation is not the same as a working path. What is known with confidence is the subluminal story, meaning the story of motion below the speed of light. That story is already extraordinary enough. It allows time to separate, distance to contract, and experience to diverge across frames, all without violating the cosmic limit. For a human voyage, this means the real frontier is not light speed itself, but the region just below it. There, the benefits and the dangers grow together. A crew might cross interstellar distances within a reduced personal time span if an immense and highly advanced craft could survive the journey. At the same time, the cost in energy, engineering complexity, radiation protection, collision defense, and psychological endurance would be severe. The universe does not say that fast travel is meaningless. It says that fast travel belongs to a demanding and asymmetrical realm where great rewards come attached to great burdens, and where the final prize of true light-speed motion is withheld entirely from matter. In this sense, the question asked at the beginning of the project receives its clearest answer only here. Reaching the speed of light is not what would really happen. Approaching it is what would really happen. The ship would experience stronger and stronger relativistic effects. The crew would live through a shortened proper time relative to the outside world. The road ahead would contract. The sky would distort. The forward environment would grow harsher. Every system of the vehicle would be tested by rising demands. Yet the speed of light itself would remain ahead, never overtaken, never matched by the massive craft, however advanced its design. The limit therefore keeps its full meaning to the very end. It is not defeated, it is revealed. What begins as a number in physics becomes, through all the inner layers of the journey, a principle that governs motion, perception, survival, and the fate of the voyage itself. A human-made object can come ever closer to that principle's boundary, and in doing so can enter a deeply unfamiliar relation with the universe. But the final truth remains steady. Matter may approach the speed of light, and in that approach almost every aspect of travel begins to change. Matter does not become light. the boundary stays intact, and the real story is the profound transformation that occurs on the way toward it, not an arrival that physics does not permit. The journey grows quiet at this point. The ship continues forward through darkness, carrying its clocks, its shielding, its stored warmth, and the slow interior life of the people within. Outside, the stars remain scattered across distances too large for ordinary feeling, yet relativity has changed how those distances are lived. Time has not broken. Space has not collapsed. The universe has only shown that motion near its fastest boundary is different from what slower creatures first imagine. A beam of light crosses the void in its own lawful way. A vessel of matter follows another kind of path, slower, burdened, and finite, yet still capable of reaching farther than common intuition once allowed. That is the calm truth resting beneath the dream. Light speed is not a destination for human bodies and machines. It is a limit that teaches them what they are. In that teaching, the cosmos becomes both larger and more intimate. Larger because its rules are deeper than simple distance and simple speed. More intimate because every clock, every breath, every glancing photon, and every thin grain of matter along the route takes part in those rules. The grandest voyage is governed by details as small as an atom and as universal as space-time. So the final image is not of a ship breaking through a brilliant barrier. It is of a ship still travelling, still approaching, still held within the order of nature. Its people age by one measure, while distant worlds age by another. Its path shortens in one frame, while history lengthens in another. And always, ahead of it, the speed of light remains exactly what it was from the beginning, not a promise to be fulfilled, but a boundary by which the universe quietly keeps its shape.